So I just want to cover some of those, show them in action a little bit before we get going some of the rest of the Stardog features. So the first one we're going to talk about is the ask query. You'll see it's a lot like a select query in that you have the triple patterns. But in this case, all you're going to get in response is a Boolean value. So in this case, I have band is a band that has, and then there's a song that's been written by that band. So all you're basically doing with the ask query is there at least one binding in the database that will satisfy this query? So if I pull this up in Studio on our music database, I can run it and I'll just get a true, because obviously there's at least one song that's been written by a band in our data. But this is sort of if you have a really complicated select query with a whole lot of joins and a whole lot of other nonsense, and maybe it takes a long time to run, and you just want to make sure the query is right, instead of actually running it to try to pull all the results back, you can just switch over to an ask, just to make sure that you're actually getting the stuff you want. That's kind of the main use case I've found. Or if you just care that there is a result, don't necessarily care what the result is. This is a much quicker way of doing that. So next would be a describe query. And there are a couple different ways to do this. You can say just describe and give it an IRI. And actually, the way the spec defines describe, it defines it as completely implementation specific, which isn't necessarily that helpful. The way Stardog will do it, if you say describe the Beatles, it will give you back just a block of RDF. So I'll actually show that in this case. If I say describe the Beatles, I get this block of turtle that contains all of the triples in the database that have the Beatles as a subject. So it might also give you the triples where the Beatles is an object. I'm not 100% sure about that. I don't remember if this data has those right away, but yeah. So if you just want to see, at a glance, what information do we have about the Beatles, without having to write a whole big select query, you can just say describe it. And alternatively, and I think this is the same. Yeah, so here we're describing a variable. We give it some triple patterns to match in a where. And it will still output a block of RDF. In this case, it basically does a describe on all of the bands whose name contains the word the. So you can see actually quite a few of them in here. So that's just an easy way to kind of get some of your RDF out. If you were trying to make, like a subgraph, or split your data off into another database entirely, you could just take the output from a describe. That'd be a pretty quick way to get some of that information exported. In a similar vein, you have the construct query. It's similar in that the response from this is also going to be RDF. The difference is you get to kind of dictate what that RDF is going to look like. So if I take this first one here, band is a band, it has member. So kind of the first thing you can do is change that to a select star. You'll see the results. So I've got my band, I've got my member. But if you change that to a construct, what you'll get is a turtle representation of those results. So for each band, where band is a band, you get that triple in here, and then all the member triples as well. And so this is useful for, you could then export this RDF, import it somewhere else, or use it wherever else you might need that RDF. It's a little bit easier to transport the RDF results versus the select query, the table. It's a little bit less standard of a format. And hopefully that makes sense. So you don't have to do a construct where. You can say construct and then give it a pattern where. So in this case, you're still doing the select on this to get those the results that we saw. But then instead of the RDF matching these triple patterns here, you give it new patterns. So for every binding that the select returns, basically, where you get this member variable, it will give you a triple for member, a band member. So I run here and I just get a bunch of IRIs defined as band members. So you can kind of make that construct block as simple or complex as you want. It's just a way to take the RDF that's existing in your database or in your virtual graph, as we'll get to a little bit later on today, and construct new RDF off of it, whether you want to then insert that back into the database or into another database, kind of whatever you want to do with that. But it's a fairly easy way to take your existing data and make new data out of it explicitly. So next, we go into SPARQL updates. So these are, instead of just the read queries like we've been working with, these are your, again, your updates, there is a great word for that I'm completely forgetting, but the create and update delete part of your regular CRUD database. So the simplest version here is your insert data or delete data. So you just write the keywords insert data, and then inside your curly braces there, you basically just give it some turtle. And do I even have that? I do have that. Oh. Okay, so I don't have this in Studio, it turns out. But obviously the insert data is just going to insert those triples into your database. Delete data, pass it explicit triples, it'll get rid of it. So really, really straightforward there. I mostly use this for testing. I guess if you were writing some kind of ETL process, if you were doing something, making turtle out of it, you could just do an insert data query. If you didn't want to go through the hassle of opening up a transaction and actually passing in the RDF file itself. So those are really simple. This is a kind of a more general insert query. As I was saying before with the construct, if you write a construct query, it spits out RDF that you could then reinsert back into the database. Well, you wouldn't really have to do that. Just change construct to insert. So this will construct that member, a band member turtle that we saw from the construct query, but instead of just outputting it to your results, it will actually insert it into the database. So if I run real quickly, I'll write where this time. Member, a band member. So I get that. I don't have anything in the database for that. If I do an insert on that, then I get a successful query. And now I have that explicitly in my database. So again, pretty straightforward, but very useful. Also, along the same lines, there's a delete query. Actually, it's a delete insert query. The insert part is optional, but so I say delete, I give it a triple pattern. It'll use the where to bind all of those things. But then if that song length seconds triple is in my data, then it will delete that, and then it will insert in that order the song length duration. So what is this query doing, essentially? We'll know that, I really wish I had multiple tabs available, but either way. A song is a song, and length seconds. You might remember seconds there is just an integer value of the number of seconds. But XSD does provide a duration methods. So in this case, we have this, we can take our seconds data and actually create a duration type off of that. So you can see versus 274 versus an actual duration that says 24 or 274 seconds, which is, technically speaking, more accurate than just a number. It requires, I guess, less implicit knowledge of the schema. Obviously, you know what a duration is in this case. And so if we want to take this data out, the seconds, and replace it with this duration, we can run this. So we have the select and the where here. We're binding exactly this query that we just ran. We're taking that. Anytime we see song length of the seconds variable, we're going to delete it, and instead we'll insert song length duration that we calculated. So running that, it doesn't take too long. Now if I run, I don't need the bind anymore. If I just run our original select query, I get that duration value instead of the integer value. So some pretty powerful stuff you can do here. Again, the insert part is optional. You can just say delete where if you don't explicitly know which triples you're going to delete. Like you could do a delete data if you knew the explicit values, but if you just want to delete matching some pattern, you can do that. And you can also add the insert to insert something in its place. So kind of the other concept that we want to cover is the concept of a named graph. So, right, so far everything we've seen, we've just been constructing our graphs, our databases, as just a set of triples, and we've queried over all of them. There is kind of a fourth component that's sometimes called a named graph, sometimes it's called a context, but you can identify a set of triples inside of your graph using a specific IRI. So it's, so you're sort of lumping them together. It's a way to make separations in a way of your data. We already said that a data set is a collection of RDF graphs. So there's one graph that we just refer to as the default graph. Some APIs refer to it as like the null context, or if a triple doesn't actually have one. In our case, we don't actually on the back end have the concept of a triple that isn't in a graph. It just goes in the default one. That default graph might be empty. You could load everything into a named graph, in which case your entire graph is a collection, therefore, of subgraphs, each of which has its own IRI that's unique within the data set. And you can query just specific named graphs. I'm sure I have some example in here. So we take our turtle here. This is a format called trig, which is just turtle, except it adds named graphs. So you can see I'm creating a graph called artist, and in that I have my triples about the Beatles being a band and the makeups and all that. And then in a separate named graph called album, I have the album information. So you can just query across all of these named graphs, which is basically what we've been doing. But if you want to have the data separate and then only query across the graphs when you want to, this is a good way to do it. It's a good way to like separate your data by source or really by anything that you want. It's also a very big use case that we've set up named graph security. So you can set up various users and roles in the Stardog system, and you can specify permissions to specific named graphs. So if I have a user and I only give him permission on the artist graph, he can try to query the album graph and it will just give no results. Even though the data is there, if they can't see it, it will be as if it's not there. So that's definitely something that some of our bigger customers will use, especially in like the financial industry or really any industry where you have privileged information. They want to have it all together in one place, but then you have to keep it separate based on what kind of user you're talking about. So we're querying named graphs in SPARQL. So in this case, we just have a regular select query. And if we have just the regular triple patterns in our where, like we've been doing, that will look in the default graph. We can also specify using the graph keyword. You can say graph, some IRI, and then a little sub block in there that will only search that one specific named graph. You can also put a variable in there, say graph G with some graph pattern, and then that'll match any named graph, and you'll actually get the named graph's IRI back in your bindings. I don't know that I have any examples of this in Studio. We'll see that at some point. And we can go into more details about it later if it's not super intuitive. This named graph basically just a way to separate your data into however you want it separated. And then you can query across it. You can query across graphs. You can query just specific graphs. Yeah, so there's an example of the query in the example where we had changed our music data set to have graphs. You'll notice that in our album graph, you have album, artist, and some artist variable. And then in the artist graph part of the query, you can still reuse that artist variable. So the variable bindings can go across graphs as well. Since the IRI for that individual artist will be the same in your data no matter where it actually is. It's a good way to connect everything. And you can also override the default graph. If you don't want to specify, graph album in your query, you can just say select star from album, and then it will treat album like the default graph. Just kind of a way to make it a little bit more readable. In this case, I only want to read from that one graph. You can also have multiple froms. I don't know if that's in the next one. No. So you can say from album and from artist, and you can just limit kind of the scope of the query that way. Instead of trying to query over every graph or query over just the default graph, you can specify a list of them. And then it'll combine all the graphs that you specify in from into basically one graph and query over that. SPARQL has a few different ways to specify kind of where you're querying from. So you can see we have the from keyword that changes the default graph. From named does sort of the same thing. I honestly still to this point, don't know the difference between from and from named, even though many smarter people than me in this company have explained it to me a few times. But and then you can also specify the graph in your where block, which is generally how I do it if I'm testing things out or doing things in general, because it's easier for me to be a little more explicit about it. But from and from named both work. SPARQL update also includes a few graph management type queries. You have load, which takes in a URL that points to some blob of RDF. You can say, I want to load this into this specific target graph. You can clear the graph. You can take triples from one graph and add them to another, which leaves the source triples where they are and just move, copies them into the target graph. Copy itself is like add, but when you say copy source to target, it's going to clear out anything that's in the target graph first, whereas add keeps anything that was there in there. Move is very similar, but on top of clearing out the target graph first, it's then going to clear the source graph after it's done. So kind of add, copy, move in order from least to most destructive, I guess. And in practice, for me at least, I find that I use these somewhat sparingly. Clear may be the easiest one for me if I'm doing some kind of testing. So let's start these SPARQL extensions. So these are things that are specific to Stardog that are not actually in the SPARQL spec, but we've extended it to do some cool things. And probably the coolest thing is this thing called a path query. So it's sort of a big problem, especially in the graph space, is to find the shortest path from one node to another. So in this case, if I want to take the query that we did yesterday, where we start at Paul McCartney and then follow the co-writer thing that we defined to figure out how many steps there are between Paul McCartney and whoever. I think Tupac was probably the craziest one that he was connected to in some way. But so we can write these path queries here and say, I want to start at this variable. And in this case, we're just going to assign that variable to Paul McCartney. This was when we did our select query. You can see the property path here, where the artist wrote some song, and that song also had another writer. So if we run this, it'll chug away a little bit, but we'll see the links. So Paul McCartney goes to Michael Jackson via these bindings, and you'll see Paul McCartney, you'll see some song has the writer Paul McCartney, and that same song has the writer Michael Jackson. So essentially you give Stardog a start node and an end node. They can both be variables, so you can define as much as you want here. Give it the predicates, the paths to follow down. That can be kind of as complicated as you need it to be. And you'll get a nice little visual representation of those results. So yeah, this is sort of the same idea, except I'm specifying my start and end as specific nodes, and I kind of took out the property path here just to make it a little bit more explicit. But this is saying I want to find the shortest path from Paul McCartney to Kanye West, or in this case, I want to see all the paths. You can ask it for the shortest. There are a few different other keywords you can throw in there, but these are all of the ways that Paul McCartney is somehow connected to Kanye West. 111 is a shockingly large number in my opinion, but hey. So yeah, and actually you see some of these look the same if this binding's... Okay, so this binding is working. I don't understand. The path support in Studio is a little bit new. So Paul McCartney and Michael Jackson wrote the song Say, Say, Say. You have then this song, and it goes down. So I'm seeing these paths that look the same in this way. I'm guessing, yeah. So if Michael Jackson and Teddy Riley here wrote multiple songs together, so each one of those is going to show its own path in the results. And looks like I have another one here. Yeah, so if I don't know the, say I don't know the IRI of Paul McCartney, I can specify in my via clause here. So some song has some writer whose name is Paul McCartney, the string, and that'll give me, it should give me the same, it gave me 112 results, so it might be a little bit screwy in there, but the same, you give it a node, or you can give it a literal value here, as long as somehow you connect that literal value to something that Stardog can query on. I don't know if anything else is really on here. So some of our other slides have more to say about path queries. If any of you are particularly interested, we can spend a lot more time in subsequent days on those. Stored queries, it's kind of annoying if you're going to reuse a query, to have to type it in every time, especially back when all we had was the command line interface. Studio makes that a little bit easier. You can load up, .SPARQL files and run them that way. But you can also store queries directly in the system itself, just with the CLI command, or in the case of Studio, they have a nice little interface down here. So if I really like this query, I can click on store and store it right to my system, whatever. So it'll show up here. I can pull it back up and run it that way. So any amount of like these stored queries, they can be stored at a system level so that you could then pull them up and run them on any database, or they can be stored at the database level. So keep them as specific as possible. Obviously that one came from somewhere else and isn't relevant, but that's how that works. And you can just execute the query by typing its name in the command line, or obviously pulling it up in Studio that way. We also allow for stored functions. So in this case, you can see we're defining custom functions based off of existing SPARQL functions. So SPARQL already has the factorial function, where you pass in a number, it gives you that number factorial. So here we're defining permutation. It takes two inputs, and using the existing SPARQL functions, it will it'll compute a new result. And then we can call permutation in our query, like we're doing at the bottom there when we're binding that value. And in the case of that combination, we can use our custom defined functions alongside the SPARQL defined functions to create new custom defined functions. This is similar to a macro definition. These also get stored in the database. I guess the slide doesn't actually say how that's done. There's a command line command that will let you save that stuff in there. We also support GraphQL, which is kind of the hot new thing out of Facebook for their graph query language. Of all of the query languages, I guess, well, because Facebook, I guess, that's the one that's kind of been taking off. It's obviously very JSON based, so a lot of people, especially used to the front end of things, see that as a lot kind of easier to learn, more intuitive. As you can see, if you kind of know the schema of your data, you just make a little JSON document looking thing. So it says, I know I have albums, I want to get the albums, and then for each album, I want the name and date and artist. You send that off, and it gets you a bigger JSON response that has the same general shape as the request that you put in. So we do supply a GraphQL endpoint. In this case, we're using an open source program called GraphQL to display the results. You can also use the command line, and I don't think, so Studio does seem to have support for GraphQL queries. I don't have any to run at the moment, but it would look very similar to this, but easier than trying to download GraphQL, I guess. So first thing we want to talk about is reasoning, and this is probably the biggest feature that we offer. People that are used to designing ontologies, and especially like in academia, it's a big thing, are used to like the concept of a reasoner that they can run on their ontologies, but we happen to have written one of the best ones that out there, and we've baked it into our product. So what reasoning does is it takes the triples that are stored in your Stardog databases along with an ontology, which we'll talk about a little bit later. And I think actually one of the days we have set up for specifically a data modeling presentation. Essentially your ontology is a set of rules that apply to your data. And when you request reasoning, Stardog will take that ontology data along with the data that's in your database already and make inferences off of it. I guess as a quick example, right, if you have an artist that wrote a certain album and there's a song on that album, you could say in your ontology, if I have a song that's on an album that was written by an artist, then I want to assume that that song itself was written by that artist. So you don't have to have that explicitly in your data. You can make the inference based on the set of rules that you provide. It's also important to note, while some systems will do reasoning by taking your rules, executing all of them, and then inserting those triples, materializing them, the way Stardog actually does it is by query rewriting. So I write a query and I tell it to use reasoning. It'll take the rules, figure out which rules it needs to use to satisfy my query, and actually rewrite it on the back end so that, at any time if the rules change, you don't have to do like a re-import of the data. It'll just use the new ones when it rewrites the queries. So what am I talking about? It's kind of we already covered a little bit of this when we went over RDF type. But so the RDF has the concept of a class, which is just a set of instances with common characteristics. So we've already been using classes this whole time. When we had, please please me is of type album. Album there is a class. Or artist is a class. Now, our classes are then organized in a hierarchy. So in the case on the right, you can see we have our class artist, and then we split that into subclasses where solo artists and some are bands. And again, there's no reason why something can't be both of those things, but in this case, it doesn't make practical sense. And so when you have instances in your database, it'll take the hierarchy information based on those properties. So if I have somewhere in my data, that the Beatles is a band, the reasoner will then see that since a band is a subclass of artist, that if I ask for all the artists, it'll give me the Beatles, even though I didn't explicitly say the Beatles are an artist, because I said they're a band. Then it'll use that logic to say they're also an artist. Similarly, you have properties, and these represent the relationships. So your classes are for your nodes, and the properties kind of describe the edges. There's two different kinds of properties. You have an object property that maps a resource to another resource. So in this case, like member is our property, and that links bands or that links the solo artists to the bands that they're a member of. So those are both class types. You also have data properties, which is taking a resource and linking it to a literal value. So an example would be like the duration property that we had on songs that takes the song entity and links it to just the literal integer value or the duration value of the song. RDFS, which is the RDF schema type, lets you specify the domain and the range of your properties. In this case, so the domain says that anytime we're using this relationship, it has to, the subject of that triple will be this of this class. Range says the object of the triple will be of this class. So in this case, we have that member relationship. So we know that if I have, the Beatles member John Lennon, because I've specified my domain and my range, I now know that the Beatles are a band and that John Lennon is a solo artist. So again, just by defining the domain and range, my reasoner can figure that out, even if I don't have something explicitly saying that John Lennon is a solo artist. So just want to give a few examples of how some of this inference works. There are a lot more examples we can go into. Again, there are, I think, entire training modules based off of this stuff that we can get into if the desire is there. So I have here a very small subset of my music graph. In this case, I actually only have 4 triples, it looks like. I have this Queenie Eye song written by Paul McCartney and Paul Epworth, and then I have Rolling in the Deep written by Adele and also by Paul Epworth. So each of those arrows there represents 1 triple in my database. So this is all the explicit knowledge that I have, but using an ontology, I can infer a whole bunch of other stuff. So if I first start by saying, well, I know that song, writer, artist is one thing. What if I want a relationship going the other way? I can just define a predicate writer of as the inverse of writer, in which case my reasoner will see things like Rolling in the Deep, writer Adele, and it will say, okay, well, then I know Adele is the writer of Rolling in the Deep. And any of those dotted lines that you see in the picture are completely inferred information. I can also, through what is called a property chain axiom, which is really deep into OWL, basically define that co-writer relationship that we were finding earlier based on paths and on property paths and all that good stuff. Basically, if 2 people both wrote a song, we're going to link them together with this co-writer property. So we have that too. If I then want to say, well, if 2 people have co-written a song, we're just going to say they're connected to each other somehow by saying that co-writer is a subproperty of connected to. So you can see that purple showed up. Anywhere we have co-writer, we can also infer connected to. But we want to say, connected to, if Paul McCartney is connected to Paul Epworth and Paul Epworth is connected to Adele, it kind of, logically speaking, Paul McCartney then is sort of connected to Adele in some way, some number of hops away. So if we define connected to there as what's called a transitive property, then it'll make that for us too. So just from those 4 triples, and then like these 4 rules here, you can see all the different inferences that have been made. And we don't have to store any of that data in the database. The reasoner will figure it all out for us. And we could still write, I want to see all the people that are connected to Paul McCartney. You can just write a query using that connected to predicate, turn the reasoner on, and it'll give you all of those triples. So we also allow these things called Stardog Rules, which is, it's kind of in my opinion, a little bit more intuitive of a way. You don't have to learn OWL You don't have to know what a symmetric property and a transitive property and all that is. This is just a pretty simple if-then. So I write a block that says if. So if I have some song that's written by some artist, and that same song is also written by the co-writer, I can put my filter in there to say make sure they're not the same person. So if I have bindings that satisfy that if block, then I can infer that artist and co-writer are co-writers of each other. So we're kind of taking that logic that we did when we were selecting the co-writer via just a select query, putting it up into a rule, and then we can just query using that co-writer property instead of having to remember kind of how we derived it in the first place. So yeah, Stardog Rules, very big. You can do a whole lot with these, and very, very useful. So the other kind of super important thing is not only do we provide the reasoner, but we also, the reasoner is also equipped to explain to you how it inferred something. So if we go back to our graph here, we can see that it made the inference that Paul McCartney and Adele are connected to each other. And so if we're writing that in a query, we see that, and we're like, okay, well, how exactly does it know that? Well, it'll tell you. So if I tell it to explain, I give it that triple Paul McCartney connected to Adele, then you can see kind of from the top down, it starts with the inference that it made. And it says, well, I know that connected to is a transitive property, and I have inferred elsewhere that Paul McCartney is connected to Paul Epworth, and Paul Epworth is connected to Adele. So taking those two inferences, it can then assert, or it can then infer, that Paul McCartney and Adele are connected. And you can see each of those sub-inferences, it tells you, well, because we have asserted these four things, those were the explicit pieces of data in our database, and you can basically see how it decided what it decided, which is especially good if you're running your queries and you're seeing results that you shouldn't see. Say like, well, I know that these two people shouldn't be connected. Well, Stardog can tell you why it thinks they are, and then that will help you see either there's some weirdness in the data or some weirdness in the ontology that caused Stardog to make an incorrect inference, and then you can fix it. Instead of just trying to go through yourself and figure out what's going on, it will just happily tell you. So the next thing I want to talk about is virtual graphs. You've probably heard me mention that a decent number of times, just yesterday and even today a little bit. So what virtual graphs do is they let you sit Stardog on top of existing data and query it in place via SPARQL. So you're not taking your Oracle database and exporting it and importing it into Stardog to query from it. We let you basically, that Oracle database can just sit where it is. You can write SPARQL queries for that data. You give it a mapping, and so Stardog will take that mapping, and then it will take your SPARQL, use the mapping to convert it into a SQL query, and then it will query that Oracle database directly. So as the Oracle database is the underlying data source, it gets updated. Stardog doesn't have to care about that because it's just going to write that query and let you query it in place. So all you have to do is give Stardog the JDBC driver for your relational database, the credentials, obviously, and a mappings file, which we'll go into a little bit of how that works. You can see we support many different relational databases from Hive to DB2, SQL Server, MySQL, all that good stuff. Also, some NoSQL databases like Cassandra and Mongo are supported. And we even have the ability to take a CSV file and provide a mapping and take that CSV file, load it into Stardog. You can't query the CSV file in place because it's not just going to look into the file system like that. But it lets you take even very large CSV files. I had a customer last week sometime that was loading a CSV file that was like 250 megabytes or something. It had 200 and something columns and like a couple million rows or something completely crazy. And they were, you write the mapping for that once, and then Stardog will just do its thing. So we're just going to show a concrete example of how the mapping works. We'll explain some of the intuition behind it, and then we'll go into the syntactic details of it. So here I just have a pretty typical relational database that's still based on the Beatles, where each table generally represents one type of entity, and then the rows of the table represent instances of that type. So this is the case for that artist table that we see on the right. We have 3 artists, each with an ID and some kind of type that has some meaning somewhere. So typically, when we're mapping an RDF table, you have an RDFS class that corresponds to that table. So in this case, you can see artist in the upper right. Each row of that table then is mapped to a node that is an instance of that type. In the artist table here, we actually have 2 different types, the 1 and 2 for solo artist and band. For now, we're going to ignore that and just assume that we'll use artist as the type. So in the mappings, there is a property that corresponds to each of the columns in your table, and then the values of the row become nodes that are linked to the entity node using that property. So you can see we take John Lennon, we take his ID 1, and we craft an IRI in our data that's just artist 1. We're using that ID column, taking the value of that row and making the URI based off of that. So we know that artist 1 is the type of artist, and we know the name, because of the name column, is John Lennon. So we just put that in our mapping. Usually if a column is associated with a foreign key, then that'll be mapped to another IRI. Most of the other columns are going to be mapped to literals, like we see with the name column here. So we constructed that artist node via an IRI template, which is like an IRI, but then it includes the variables, like in this case ID, that'll be replaced with actual values. So we're just concatenating the local name artist with the ID column value of the artist table, which you can see from the curly brackets, which identify the table columns. Just a colon at the beginning there indicates that the IRI belongs to the default namespace. And then the combination of that namespace, the local name artist, and the primary key ID is making sure that that artist IRI isn't going to clash with anything else that we might construct for other tables or external data sources. So that's our simple mapping from the artist table here. We're going to add on the album table, which we map in a very similar way by creating one node that represents the album, again, using the IRI template of colon album and whatever the album ID is, and then literals for the name and the release date columns. But in this table, you see we have the artist column, which is a foreign key, to that artist table that tells the artist that released the album. So when we're mapping that foreign key column to RDF, we use an IRI template the same way of colon artist and that ID, but because that's using the exact same template that we did for the artist table itself, it naturally is going to link those 2 nodes together because it'll generate, given that ID, it will generate the IRI the same way. So that's how you get the album ID is linked to the artist via that artist predicate. So using the same template, both mappings will refer to the exact same node, and that's how you get that connection. So we can map the song, or the tracks in this case, which is another foreign key reference. The difference here is that in our schema, that track property goes from the album to the song and not the other way around. So we have the track that has that album foreign key, but you can see we had to specify the direction of the track predicate there when you're doing your mapping. So because direction is obviously important, but we map the song with song ID, we have the type, we have the length and the name just from the columns, and then the link to the album table. So noting that, as you can see, the more tables here that we map to RDF, it takes the implicit graph structure that's kind of hidden in the relational model and makes it explicit. This songwriter table that we have here is different from the other tables because none of the rows in it represent entities. This is what's known as a junction table. So the conventional way to represent many-to-many relationships. Sometimes they're called bridge or associative tables. So in the songwriter table, each row is just representing a link between a song and the artist who wrote it. So you just have the IDs or just the foreign keys. So the Love Me Do song, identified by number 1, has 2 writers, which are the artists with ID 1 and 2, which correspond to John Lennon and Paul McCartney. So each row of this table is then mapped to a single triple in RDF, which you can see kind of along the bottom there. It's taking song 1 and linking it to artist 1, or song 1 and linking it to artist 2 from that writer predicate. So each of these tables, therefore, we write some amount of mapping, and then when you put them all together, you can see how the graph kind of comes out of it. So there is an actual standard way to represent this. It's called R2RML. So this is sort of taking the actual mapping that we just went over and in R2RML. So you can see it's very turtle looking. It's got some blank nodes in it, and it's really kind of, at least for me anyway, kind of hard to look at. It's especially hard to figure out exactly what it's doing unless you are already familiar with R2RML, which I wasn't. So fortunately for me anyway, we offer kind of an easier way to do this, which we call the Stardog mapping syntax, or SMS. I think behind the scenes, this just gets translated into R2RML. So once you have it loaded in your database, you can export the R2RML if you wanted to actually have the standard. This, at least to me, I guess coming from more of a RDF background, this is a lot easier for me to figure out. So we have 4 different pieces of Stardog mapping. First is the keyword mapping. You can optionally give it a name or an IRI. You give it an input table. So in this case, we're going to map from a SQL query, which is, in this case, just select star from album. You can have any kind of SQL that you want in there that will go directly to the to the relational database. And then you give it an output graph. So input table, output graph. So when I select from the album table, I'm going to get things like name and release date, which are columns in that table directly. So I can just reference them directly as variables. But I also need to, make my album IRI and my artist IRI, which happens down here in the value mapping. So I take ID, which is a column, and artist, which is the 4th column, and I can bind those to IRIs, stardog.com/tutorial/album, whatever the album ID is, call that album the variable, and I can use that in my mapping. So when it does a select star from album, essentially for each row that it finds, it's going to take ID, artist, name, release date, bind them where it needs to bind them, and then you'll get essentially each day version of this output graph in your graph, and it'll do that for each row. So when you load this mapping in, it'll do that, and then you can write SPARQL queries that use these, name, artist, date predicates, and then behind the scenes, Stardog will rewrite that into the SQL query it needs to use. So you can register a virtual graph via the command line. You can see I just do an add, and I give it a properties file and then my mappings file. So we already kind of covered the mapping. Properties is pretty easy. You can see at the bottom, at a minimum, you have to give it the JDBC credentials. So a URL, the JDBC URL of the specific database that you need it to query, username and password, and then the JDBC driver. You just need to make sure is on your Stardog class path so that Stardog can find it, and it will take care of actually doing the JDBC connection there behind the scenes when you query your virtual graph, which in this case will just be called music because your properties file is music.properties. See, and then to query it then, once I've loaded in the music virtual graph, we have kind of a special syntax. It will basically load the virtual graph into a named graph in your database. So if I'm writing a query, I query from the named graph virtual : / music, and query it like you would any other named graph, and just either know that behind the scenes it is taking what you write in SPARQL, translating it into SQL, and querying that relational database live, or you don't need to know that. That's just what it's going to be doing. So you can basically seem like magic. I'll reiterate again that the relational data stays where it is. We're not doing any kind of import to get this data into Stardog, so you don't have to worry about it being stale or anything like that. It'll do a live query every time it needs to, at least, to the live data source, without having to really do anything to that live data source, which is pretty good stuff. This next thing I want to talk about is, so that was kind of unifying the structured data, our various databases, data silos, all that good stuff. But what about the unstructured data? What about PDFs and Word documents? And a lot of the big enterprise data is going to be stored in these PDFs and Word documents, and things that aren't just going to nicely fit a schema that we can tell a computer how to deal with. So we have a system called Bytes, which stands for Blob Indexing and Text Enrichment with Semantics, for what that's worth. You can see on the left there, you have the PDFs and the Word documents go into Bytes when you tell it to load the document. So kind of the most basic thing that Bytes will do is it'll take that document itself and store it in the file system of the Stardog server. It's either the local file system that the server's running on, or even something like Amazon S3, or wherever you feel like storing those documents. It'll store kind of a copy of that document. It'll also then extract some of the metadata from it, especially true with like a PDF. PDFs store a lot of metadata on the files itself. So things like the creator of the file, the length of the file, or the type of the file, all that stuff. It'll extract that and serialize it as triples, put that in the RDF index. You can also scan through the actual text of the document itself, run that through a text extractor, and that data will go to one of two places. It'll go through some RDF extractor that's either something like, I think Apache Tika, I think, is the one that we use out of the box. Something that'll take that text and extract some kind of RDF meaning from it, whether that's extracting entities, extracting entity names, trying to link things together. So you can run it through that, and you can even write a custom extractor, which I think we can go into at some point. It'll put all that in the RDF index, but then it'll also just take the text of the document and put it in a full text search index. So we support Apache Lucene for doing full text search. So when you load in an unstructured document like that, it will automatically put that into the text index so that you can then use the full text search, try to find information from it that way. Yeah, so I think I already talked about most of this, storing the document itself and the metadata. Storing the text is optional. If you don't give it to any kind of text extractor or entity linker or anything, it won't try to do that. We also support OpenNLP for natural language processing. I know we have some examples of that. I don't think they're in this slide, but we can go into that at some point if people want to kind of parse through the text of the document, figure out something like names. It'll scan the document looking for names and pull those names out, link them to entities that are in your data, all kind of automagically doing that. You can query Bytes the same way you query really any named graph. So we're just writing the query against a named graph that has this special docs tag URN attached to it. So this is the yfp90.pdf. We'll say that we loaded that document into the Bytes system. We get back that tag, and we query that as a named graph. And we should just see SPL. So this is all of the metadata that was stored about that document the instant we loaded it in, including it's a typed document, you have the file size, label, PDF version, all that good stuff. Anything that it could find in the metadata, you can then query. And recommended reading, we have a whole big Bytes section of our docs, and I think also a couple of Bytes tutorials on the website if you look around in the tutorial section. So
and that's sort of a, sorry, Stephen, just to chime in, that's a little bit of an Evernote or evergreen comment, right? Is that our docs are sort of outrageously thorough from a technical perspective. And so would obviously encourage folks to, and we'll be sure to follow up with links and so forth, but for basically all the key tenets that Stephen's been hitting on, all of those are covered in sort of painstaking detail in our documentation. So just a good thing to note.
Yes, as the head of technical support, please, please, please read the documentation. So I think this might be one of the last things on here. So we have this thing called integrity constraint validation, or ICV, which is similar to reasoning in a way. If you remember, with reasoning, we defined some rules that said, if you have this, then you can infer this. But what ICV does is it switches that context from what's called the open world assumption to the closed world assumption. So these are kind of like basic tenets of, I guess, the semantic thinking in general. So we default to the open world assumption, which says just because we don't have data in the database doesn't mean that that data doesn't exist somewhere. So if I have the band The Beatles and I don't have a triple in there, I don't have anything that says they're a band from the 60s. Open world assumption means they still could be, because I don't have anything telling me that they aren't. The closed world assumption assumes that all of the data I have is all of the data there is. So if I don't have something, that's because it's not true. So the simple example of this is if we have our rule, if X is of type A, then X is of type B. Then if I have the data that says, well, I have this thing called foo, and that's of type A, from the open world assumption, we can then say, oh, well, if foo is an A, then it's also a B, because that's what your rule says. But the closed world assumption says, okay, you said foo is an A, but you never said foo was also a B, and it's supposed to be, so that's a violation. So kind of the ontologies and reasoning is a way to take data you have, make inferences from it. ICV says you tell it how the data is supposed to be, and it will tell you if it violates something like that. So yeah, again, if you then put in that foo is type A without also having it be type B, then it'll report that as a violation when you do an ICV report. We also have what's called guard mode. So the default mode is just on demand. Tell me if the database is consistent. What guard mode does is anytime you would add or change data to your database that violates one of these constraints, guard mode would just say no, and it would roll the transaction back and not let you make your database in an inconsistent state. And we have a whole API for explaining the violations, similar to how the reasoner can explain how it gets where it's going. And also repairing them. If you have an ICV violation, you can tell Stardog to repair it, and then it will just add the data that it needs to make that, to satisfy those requirements. Sort of a newer thing that we're supporting currently in beta is a standard called SPARQL, which is the shape constraints language. It's kind of similar to ICV in that you define shapes for like the various nodes in your data. I don't have a real solid example of SPARQL here, but say you can define a shape that says, if I have a node that is of this class, then it should have at least one of this property. The property should be in this range of values. It shouldn't have this property, and you can specify all of that and the shape that node is supposed to take. And then you can do an ICV report and get a SPARQL report that says whether your data is in compliance with your SPARQL shapes or not. Again, it's a W3C recommendation at this point, but it's a way to validate the RDF graphs against a set of conditions. On demand, ICV can put out a SPARQL report. And again, that's sort of constantly in flux as the beta goes on. We do have a couple of users using it in earnest, reporting back to us. There is a piece of it called SPARQL Rules, which is not part of the W3C recommendation. I think it's just a proposed thing at this point, so we do not currently have any support for that. But again, we can go into any more of this detail. We're getting SPARQL support into Studio as we speak, and so people will likely ask about that going forward.